Okay, so now we're moving on to topic 3, our final topic. So this is matrices. A matrix, at least the matrices we work with, is usually a two-dimensional array or sequence of items. Now, these items could be numbers, expressions, letters. You could have a matrix that looks like this of letters. You could have a matrix that looks like this of numbers. This is almost a one-dimensional matrix because it only has sort of one direction through it. Now, what do we use matrices for? It's sort of like think of it like a sort of mathematical structure that we can use for modeling certain things. We can use it for modeling competitions, solving simultaneous equations, and doing transformations with data and working with vectors. Sort of a higher level thing that is used in very high-end mathematics, even cryptography and such. So let's look at how we do some operations on these matrices. We can represent a matrix sort of like, let's just give it usually a capital letter. I don't really ever see a lowercase letter. We give it a capital letter and we say this equals, and then we define the matrix. So let's do this matrix. Now, when we multiply a scalar by a matrix, we simply have to multiply each of these items, each of these elements inside the matrix by that scalar. And that's all we have to do. Oops, my mistake. Now, this is commutative when you multiply scalars. When you actually multiply two matrices, it's not commutative. So we'll go over soon like how complicated it can get multiplying two matrices. This does not equal this. If A and B are matrices, A times B does not equal B times A. On the other hand, A times K does equal K times A. And this is sort of used in algebra as well, because we might have like A times B equals C times D. If we want to divide both sides by A, what we do instead of that, if we're thinking in terms of normal maths, we multiply both sides by the inverse of A, and we have to think about the order we do things. We tend to put the inverse at the front. So you sort of have to understand these patterns that we use a little bit to actually make our matrix multiplication make sense, because it is very fussy as to which order you put it in, and you'll get used to sort of the order that you're supposed to put things in. So there's 2 by 2 matrix multiplication. I'm going to go straight into doing 3 by 3 or something of that level. Actually, I might start a bit smaller, matrix multiplication, to give you an understanding of what is the larger process instead of just knowing like a formula to achieve it. So let's look at the two matrices. 2, 1, 3, 4. And let's try to multiply that by 4, 3, 4, 3, 2, 1. Okay. Can these matrices multiply by each other? The answer is no, they can't. And how we find that out is we look at the dimensions of matrices. And this tells us some important information when we look at the dimensions of matrices. So this matrix, we're going to call this A and we're going to call this B. A has the dimensions of 2 rows and 2 columns. B has the dimensions of 3 rows and 2 columns. If we want to see if we can multiply matrices, we like to put the first one, because this is part of the reason why order matters. We put the first set of dimensions and then the second set of dimensions. If these are the same number, we can multiply these two matrices. If the columns of A, the columns of A are the same as the rows of B, we can multiply these matrices. Now, let's actually put that into practice. So instead, let's look at this a matrix as such. We'll use B again, and then we'll multiply it by C. We'll do it like this. Make it simple. Can these matrices multiply each other? So matrix B and C can be multiplied by C. well, let's look at the dimensions of B. So we have 3 rows and 2 columns. And then for C, we have 2 rows and 3 columns. Okay, so we can multiply them because these numbers are equal. Now, then what we find is, okay, what are these outer numbers? These outer numbers describe what is the end result, what is the end result dimensions of our matrices, of our matrix, sorry, that we get from multiplying B and C. So we actually need to make a 3 by 3 matrix for this multiplication. So that's because we have 3 on the outside and 3 on the outside there. And this is rows and this is columns. So let's look at how we actually multiply these, what we do. What we do is we look, okay, we want to find what is we know that this is 3 by 3. We want to find what is in the first row and the first column. How we find that is we multiply the first row of B by the first column of C. So we do 4 times 3. So that's this 4 times this 3 plus 3 times 3. That's this 3 times this 3. So this multiplied by that in order. And that's why we have to, because of how this multiplication works, that's why we have to have these dimensions working in a specific way, because we want there to be 2 here to multiply by 2 of those. So we want the rows and the columns, the rows of number 1 to match the columns of number 2. So now let's look at, if we want, we're probably going to need a little bit more, probably going to need a little bit more space. Let's look at the column 2, row 1. So to do this, we multiply row 1, column 2. We multiply the first row by the second column. So that's 4 times 2 plus 3 times 2. That's multiplying this again by that this time. Now we want to get the row 1, column 3. So that's over here. We want to do row 1 times column 3. So that's 4 times 1 plus 3 times 1. And that's our first row. Now we want to get row 2. So we do row 2 times column 1 to get the point at row 2, column 1. So that's 4 times 3 again, plus 3 times 3 again, because this is the same. Now we want to get row 2, column 2. So we multiply row 2 of B by column 2 of A. So that's 4 times 2 plus 3 times 2. Now this will be the same as well because we have the same first 2 rows. Now we want to do row 3, column 1. So we have row 3 of B times column 1 of C. So that's 2 times 3 plus 2 times 2. And then we move forward as such. So we do 2 times 2 plus 1 times 2. And then we do, I made a mistake here, 2 times 3 plus 1 times 3. Sorry. 2 times 2 plus 1 times 2. And then 2 times 1 plus 1 times 1. And this is our result. We would go through and we would actually figure out what is the result of each of these. And then we have our 3 by 3 matrix result. So that's our general process. And you can follow this process for any size of matrix. You are just looking, if you multiply it, you're looking, okay, if we multiplied A times B, you find out what the dimensions are, and then you say, okay, row 1, column 1, we multiply row 1 of A by column 1 of B. Row 1, column 2, row 1 of A by column 2 of B, etc. So now let's look at the identity matrix. First, I just want to define, if people don't know what an identity anything is. So we have an operation. Let's say we have an operation A, squiggly line with an identity. The result will be an A. So a squiggly line could be a plus, could be multiplication, anything. But that means the identity is different in each of those operations. So think about 4 times 1 equals 4, and 5 times 1 equals 4. No matter what you equals 5, sorry. No matter what you multiply by 1, it's the same number. Therefore, it's the identity value in multiplication. Now, if we do 4 plus 0 equals 4, 5 plus 0 equals 5. Therefore, for addition, 0 is the identity. And when we do the inverse of a number in terms of a certain operation, that means we would consider what creates the identity when you do that operation on a number. So the inverse of 4 in multiplication is multiplied by 1 over 4, because that creates the identity. It does the inverse. So 5 times 1 over 5, that's the inverse of 5. In multiplication, it creates 1. 4 minus 4, it's the inverse in addition, creates 0. 5 minus 5 creates 0. So that's what the inverse would be in terms of if you're looking at identities, theories about identities. Now, an identity matrix is the same idea. You have a matrix, you multiply it by the identity, it equals the same thing. You multiply a matrix by the inverse of that matrix, it creates the identity. So an identity matrix looks like this. And there's multiple different levels, because remember, you can only multiply A by B, and this time let's do A by I, if this is true. If A's columns is the same amount as I's rows. So if A has 2 columns, you can multiply it by this. If A has 3 columns, you can multiply it by this one here, which we'll call identity 3, and this one we can call identity 2. So we can do that to sort of work with the inverse here. The inverse is basically, the rule of the inverse is you can multiply the inverse by A, and then it will equal 1. And you can multiply A by the inverse, and it will equal, not 1, sorry, and it will equal I. It will equal the identity, because it's the inverse, and that's what the inverse means. Now, the inverse we can actually find from A with this formula here. We have 1, and then down here is what we call the determinant of A. And then we have this sort of complicated factor here, which is we can find sort of differently, and there's extremely heightening levels of complication in terms of actually finding this value here, based on how complicated the actual matrix is. If it's 3 by 3, it's very difficult to actually find. So other than your graphics calculator, which you'll probably cover how to work with matrices with that in class, other than with your graphics calculator, you won't actually work with the inverse of a 3 by 3 matrix. Doing that by hand is well, not that you won't work with it, but that you won't actually have to find it by hand, because it's absurdly difficult, I guess. Now, the determinant of A, there are systems of finding that, because it's different depending on, obviously, the size of the matrix. There's some very specific systems of finding that I could recommend you looking up, like how to do it with a 3 by 3 matrix, or how to do it with any size of matrix, because it's sort of useful. It's interesting. But for now, we will just follow this formula that we can always use for a 2 by 2 matrix. So we know that the determinant is equal to this. When the matrix is equal to, doesn't write it down, but when this is assuming the matrix is A, B, C, D, like this. Now, we use the determinant, and then over here, for 2 by 2 matrices, this factor here, we can just say is, we flip basically A and D, we flip the horizontal, we flip this diagonal, and then we flip the signs of that diagonal. So D and A swap, and then C and B, they have flipped signs. And then we multiply that by AD minus BC. And that's, if you can remember that, it's useful, but also if you can look up how to find the general way to find a determinant, it still does help understanding a little bit. Remembering this, though, is completely fine. Find the inverse. So first I'm going to do the determinant. So that is 3, we have 3, 4, 9, 8. The determinant will be 3 times 8 minus 4 times 9. and that's all over for this formula here. We have to put 1 over that determinant, and then this factor over here, we flip the 3 and the 8, and we put -9 and -4 here. So that is 120 over 24 minus 28, 8 minus 4 minus 9, 3. This is my mistake here. This is 36. Now, that is we can simplify it a little bit, but this is our inverse matrix. You could optionally, if it seems convenient, actually move this scalar product into being a factor of each of these, but for now we don't actually need to do that. What is the property of A times the answer of part A? Well, the answer is I, because we know that because it's A times the inverse of A, we know that it's equal to I. So there's our answer immediately. So we can use this understanding to model a solution for simultaneous equations. And now this is very, very useful in calculator. And there's often a 1-mark question on the exam for a very annoying simultaneous equation that you can just immediately do with matrices. And it might have fractions and stuff in it to a point where it's awful to actually solve by hand. And basically, if we can plot a simultaneous equation as shown here. So x, y, z, if you put them in the right order, you can put that in there, and then you can put all these here, because you can expand this out. If you expand this out, you will be able to see that it actually results in the same thing here if you expand all these matrices out. You don't need to do that though, because we can just look that we can just know sort of that it works and then apply it during the exam. So you put x, y, z in this vertical matrix, and then A, B, C, A, B, C, A, B, C, whatever. Now, we have this basic structure that is best to memorize, and then we can actually utilize matrix algebra to do it, because we want to find what x, y, and z are. So if we put x, y, and z here, now, if this is multiplied by A, we'll call this A, and this equals B. Now, if we want to get x, y, and z on their own to find what they are, we can multiply both sides, and remember that order matters. You can't do it like this. That's wrong. If you put the inverse of A out the front, you have to put it out the front again. So we can do the inverse of A by both of these, put the inverse of A out the front of both of these sides, and you have to put it out the front, because if you put it out the back, then you're not actually getting the identity, because you're multiplying the inverse of A by x, y, z, which is incorrect. So basically, if we have A, x, y, z, which you can plot in your calculator, then we can multiply the front by the inverse on both sides. And that immediately cancels everything on this side, because you know that's the identity. So then it becomes identity multiplied by x, y, z equals the inverse of A times B, which you can just solve on your calculator. And this cancels out itself, because the identity multiplied by anything that it can be multiplied by is just the same as that thing. So then you have your answer when you figure this out on calculator, which is very fast and quick. So let's actually work with inverse matrices and the identity matrix. So let A equals this and B equals that. Evaluate A times B and hence determine the inverse of A. So looking at this, I can figure out if I multiply A times B, it's probably going to be equal to something, let's say the inverse, that tells us that B is actually the inverse. So let's say the identity matrix, sorry, that tells us that B is actually going to be the inverse of A, which is what I'm suspecting. We'll find that out. So let's multiply these together. Now let's look at their dimensions first, like we looked at before. It's 3 times 3, and then 3 times 3. They can be multiplied because these inner dimensions match, and these outer dimensions describe to us that we're going to be having a 3 by 3 matrix. Now I want to put this border all the way over here, because we're probably going to have to add a lot of little pieces. So let's look at row 1, column 1. What is the value of row 1, column 1? So we get row 1 of A and multiply by column 1 of B. So that's 5 times 2, minus 2 times 1 minus 4 times minus 1. Now we're probably going to need even more space than this. We'll leave it open. So then column 2, row 1. So we do the row 1 of A times column 2 of B. So 5 times 2, negative 2 times 1, negative 4 times 2. Now over here we're doing row 1, column 3. So row 1 times column 3. And we can continue to go down. Row 2, column 1. So that's minus 1 times 2 plus 6 times 1 plus 4 times minus 1. Row 2, column 2. So that's minus 1 times 2 plus 6 times 1 plus 4 times 2. Now, you can probably put the borders here. We have row 2, column 3. So that's minus 1 times 4 plus 6 times minus 4 and plus 4 times 7. And we can finally finish off with row 3. So we have row 3, column 1, 1 times 2 plus minus 2 times 1 plus, we can ignore the zeros because they're obviously going to just cancel out everything. So we have 1 times 2 plus negative 2 times 2. And then finally down here we have 1 times 4 minus 2 times minus 4. Now, we're going to try to figure out what this is, and we can assume it's probably going to end up something like an identity matrix because we are expecting that A times B tells us something about an inverse. So B might have some relation to an inverse. 5 times 2 is 10, minus 2 plus 4, 12. Then 10 minus 2 minus 8 is 0. We have 20 plus 8 minus 28 is 0. So I'm starting to see a pattern here. We have minus 2 plus 6 minus 4, 0. We have minus 2 plus 6 plus 8, that's 12. And then I might be able to assume that the rest of this equation, I'll just check on these last two ones. So that's 2 minus 4, but I'm probably made a mistake. And this is a good way to check your mistakes if you think you know what the answer is. So we can look down here. This is row 3, column 2. So this should be 1 times 2, and then minus 2 times 1 is actually the answer. So yep, this culminates in 0 as well. And then we have 4 times 8, 4 plus 8, sorry. So that's 12. So that means that A times B was equal to 12 times the identity. Now this means that I can assume we can divide, I can assume A, 1 over 12A times B is equal to the identity, which means I can just comfortably shift, since again, scalar multiplication is commutative, we can shift this scalar, this magnitude around. So I'm actually allowed to do A times 1 over 12 B equals I. So that means I think B is equal to, or I think that my inverse is equal to 1 over 12b. And that would be 1 over 12 in front of all of this stuff here. So hence solve the following system of simultaneous equations. So I can say, okay, B is, my inverse of A is equal to 2, 2, 4, 1, 1, minus 4, minus 1, 2, 7. And that's all. I can't forget to put the 1 over 12 out the front there. So we want to solve the following simultaneous equations. So we can put A down first. So this is what A is. Minus 2, minus 4, minus 1, 6, 4, 1, minus 2, 0. Okay. So now that's the same as what we have here. We can multiply that by x, y, and z. And then we know that this equals to 24, 12, and 0. So now, again, following this system that we're using here, following the system of finding simultaneous equations that we were using over here, that was described here, we can consider A times x, y, z is equal to 24, 12, 0. We can consider multiplying everything by this. So then we get x, y, z on its own. So that would be x, y, z is equal to the inverse, is equal to 1 over 12, 2, 2, 4, 1, 1, minus 4, minus 1, 2, 7, all multiplied by what we had on this side. So that's 24, 12, 0. So comfortably we can look at this and we can see that this is 2 and this is 1. So we would do sort of a simple matrix multiplication to finish this off, just like we sort of did over here, which this was a much more complicated one than we'd have to do here. We may as well just actually quickly do it. So we have, it's actually probably going to look sort of more like this, but we will, let's consider the dimensions first, as usual. 3 times 3, and then we have 1 times 3. So, sorry, 3 times 1. 3 times 1. So that means our final dimensions are going to be 3 rows, 1 column, which is good for us. That's what we want. And now we can find, okay, so what's in position row 1, column 1? We have 2 times 2 plus 2 times 1, and then we can ignore the 0. So then down here we have 1 times 2 plus 1 times 1. Down here we have minus 1 times, to minus 1 times 2, and 2 times 1. This is equal to 6, 3, and minus and 0. So that is the answer that we get from our simultaneous equations. We know that x, y, z is equal to 6, 3, 0. So x is equal to 6, y is equal to 3, and z is equal to 0. Now, there could be a mistake, but no, it looks like that's correct. It's very easy to make a mistake here. Luckily, there's lots of carry-through marks for questions like that in exams. So this is our final topic. We're going to look at dominance matrices. Now, these aren't very complicated. These are pretty simple. Basically, it's just a way of considering and ranking round robin competitions. So when a group of people compete against each other and each of them competes against everyone else, and then we want to accumulate in some way, aggregate in some way the wins that they all had, we can, in a very simple sense, just put them in a matrix. We can say, okay, we have A, B, C, D. We have A, B, C, D. Okay, A defeats C and D, so we put a 1 and a 1 there. B defeats A, so we put a 1 here. So this is who's defeated, and this is who defeats. C defeats B and D, so we have 1, 1 there. And D defeats B, so we have a 1 there. And everywhere else will just be a 0. So there you go. Everything else will be a 0. So Everything else will be 0. So that's probably about right. Yep. So basically what this is saying is if you just read one of these, you're saying, okay, A on the left side defeated C and D. So this represents who's defeated and this is who defeats. Now, this isn't that useful. You could look at this and say, like, okay, so that person has 2 points, that is 1, that is 2, that is 1, but that doesn't give us actually much value. What we can do instead is we can do multiple orders of dominance matrices, is what we call them. So when we multiply a dominance, when we square a dominance matrix, it does something very interesting. So if let's say A defeated B, C, and E, then if D defeated B, it's less valuable than if F defeated A, because A is more valuable to defeat in this ranking system that we're building, because A was able to defeat multiple other people. When we square a matrix, it's basically taking into consideration if you were able to defeat someone that was able to defeat more people, because the way in which if you actually like did the multiplication by hand, you'd see that it would culminate in basically you getting more points if someone you defeated, because your points get multiplied by their points. You would get more points if you defeated someone who defeated more people. And this allows us to sort of have a bit of a ranking system which takes into consideration values of someone you defeated. So this is a simple scenario of squaring this dominance matrix. Now, A has more points now because A was able to defeat C, who defeated more people than everyone else other than A. So A is winning now because the difference between A and everyone else is A got 2 points, and it was also able to defeat someone who was especially valuable. And that's basically what dominance matrices are. So when you are making a ranking with dominance matrices, you get M, which is just the simple like system we described before. That means A defeated C once and defeated D once, B defeated A once. And then you're able to add different powers, because you can keep going further and it will keep adding more. The problem is as you go up, it'll get exponentially more valuable. So you tend to add arbitrary coefficients to the front of the higher power matrices, but it is completely arbitrary. When it comes down to it, when you're using dominance matrices and you're using powers of dominance matrices, you are creating an arbitrary system of evaluating matches, of evaluating round-robin matches. And this is useful in applications of, for example, basically, usually the biggest example that I see people try to apply it to is being able to predict who will win another time based on previous wins. So you're sort of giving a ranking to how good you think someone is, therefore how likely they are to win. And that's the system of dominance matrices. So I think that mostly wraps us up in terms of content. We covered induction, so basically a way to solve things with a sort of recursive method that's able to prove for a well-ordered set that there's a consistent rule. Then we covered vectors, covering a lot of what we already covered before, and then going over some proof stuff. And then matrices, so just some operations we can do in matrices, and then the application of these dominance matrices, which are pretty simple to be honest, if you like look at them at a basic level, partly because they don't really need you to solve anything per se. Like there's not any truth towards the value they create. They're a little bit arbitrary, but they can be used to maybe like predict things. So